In this video, we'll discuss a tool called D-separation, which gives us a way to build on the properties of graph structures developed previously so that we can effectively analyze association patterns in more complex causal graphs. Causal diagrams that are used in practice are much more complex than the building structures of chains, forks, and colliders. The example here is likely still too simple a diagram for most practical settings, but it is rich enough to point out the jump that we have to make in our understanding to move from analyzing building block structures to analyzing causal graphs used in practice. In particular, note that there is one causal path, AMY, highlighted in orange, a non-causal path, AMVY, highlighted in blue, and another non-causal path, ABCY, in green. Not only are there multiple paths between the treatment and outcome, but also the non-causal paths have more than 3 nodes and seem to be combinations of forks, chains, and colliders. Amidst this complexity, our goal is to simultaneously leave causal paths open or unblocked, letting association flow through, but block non-causal paths, prevent association from flowing. Let's step through a process for approaching this. The first step is to enumerate all paths from treatment to outcome that you would like to block. Generally, this will be all non-causal paths. In our example, this includes 2 non-causal paths, AMVY and ABCY. The second step, which is also the last step, forms the bulk of the process. We want to find a set of variables that can be conditioned on to block each path, to block the flow of association along each path. We'll call this set Z and refer to it as the conditioning set. We're trying to find one single conditioning set that will work to simultaneously block all non-causal paths, rather than a separate set of variables for each path. To check if a set Z works, we must check that each path meets one of 2 blocking conditions. These conditions generalize the independence and dependence relations in chains, forks, and colliders to help us understand association flows in longer paths. The first condition is met if the path contains a chain or a fork at some point within the path, and the middle node of that chain or fork is conditioned on. The rationale for this criterion follows exactly from our discussion of building block structures. Because association flows from start to end in either a chain or fork, we can block that association by conditioning on the middle node. The second condition is met if the path contains a collider at some point within the path, and neither the collision node nor any descendants of the collision node are conditioned on. This also follows from our discussion of building block structures because conditioning on the collision node or its descendants creates dependence between A and C. So let's check these 2 conditions for our 2 non-causal paths. Let's start with the AMVY path. To check whether a path contains a chain, fork, or collider, we look at overlapping sequences of 3 nodes in a row. So in the first path, we have AMV and MVY. Because AMV is a collider and M is not conditioned on, it's not boxed, this first path is already blocked because it meets condition 2. Because MVY is a fork, V could be added to the conditioning set so that this path could also meet condition 1, but over meeting these conditions, conditioning on too many variables, is not recommended for statistical reasons. Doing so makes less optimal use of our sample size, which is the idea of model efficiency. In summary, for path 1, there's nothing to do. It's already blocked by the presence of a collision node M that is not conditioned on. Let's draw a connection to exchangeability. This first non-causal path does not contribute to a lack of exchangeability because no non-causal association flows from treatment to outcome along this path. Recall that exchangeability is the independence of the potential outcomes in treatment, which is important if the observed outcomes in each treatment group are to reflect the full set of potential outcomes for all study units. This lack of association flow between A and Y along this path is independence of YA and A along this path. Lack of exchangeability Dependence between YA and A might arise from the other non-causal path, though. Let's analyze path 2. Here we have two structures, ABC, a chain, and BCY, a fork. Because there is no collider on this path, only condition 1 is relevant. In order to block this path, we need to condition on the middle node of the chain or fork, or both. So we would have to add B or C, or both B and C, to the conditioning set. But remember, less is best. So we shouldn't add both B and C, but rather just one or the other. How should we choose? In practice, if we're using these ideas to plan a study, we should favor choosing the variable that is cheaper or easier to measure. If data have already been collected on both, we should favor conditioning on the one that has been measured more reliably. If that's a tough call, then it's always possible to choose both in turn and see how downstream results are affected. Let's again draw a connection to exchangeability. This second non-causal path does contribute to a lack of exchangeability because non-causal association does flow from treatment to outcome along this path. This association flow between A and Y along this path is dependence of YA and A along this path, which is exactly a lack of exchangeability. However, we can recover conditional exchangeability by conditioning on B or C, or both B and C. So, in conclusion, our conditioning set Z is a set of variables that can make the treatment groups conditionally exchangeable. In our example, Z must contain B or C, and it has the option of containing V. So in order to block the two non-causal paths in our causal graph, the set of variables to condition on can be any one of these 6 sets. The two single variable sets, B and C, are the minimal conditioning sets and are preferred for reasons of statistical efficiency. The process of listing paths to block and checking blocking criteria is called D-separation, where the D stands for directional. In a general directed graph, and not necessarily a causal graph, two nodes X and Y are said to be D-separated if all paths between them can be blocked. If not all paths can be blocked, then X and Y are said to be D-connected. In a causal graph, we use D-separation to find a conditioning set that specifically blocks all non-causal paths, so that only causal paths are creating association between treatment and outcome. In this way, we can achieve conditional exchangeability. This means that we can condition on, hold constant, the variables in the conditioning set and compare observed outcomes between treatments fairly. Regression modeling is one way to do this, and we'll make that clear in the next video.